Everyone, I'm Sultan. I worked on examining the PowerG wireless protocol, which I'll be telling you about shortly, together with my colleague James. I focused mainly on the RF side and some of the initial reverse engineering, and then James kept going with the reverse engineering to figure out the protocol. Unfortunately, he couldn't be here to present with me in the talk, so I'll be covering both our portions of this. We are both from the hardware and embedded systems team at NCC Group. We do consulting on hardware security on all sorts of products. So a lot of you are probably wondering first, what is PowerG? You probably have never heard of it. It's a proprietary wireless radio protocol that was developed by Johnson Controls for use in their wireless security systems and in safety systems too. Most commonly, it's used in alarm systems for homes. It interfaces with things like door sensors, window brake sensors, motion sensors, alarm sirens. It also supports smart locks controlled by this protocol, and all these devices will interface with a central panel device that controls it. You can also have fire alarms that are built on this system, and again, the various sensors will report fire status to it, and there are sirens that are also supported with this protocol. PowerG is a protocol that has frequency hopping and adaptive transmission power for energy saving, and it has some forms of encryption for security and reliability. Johnson Controls tends to advertise this protocol as their most secure radio protocol, and they consider it one of the most secure radio protocols on the market for alarm systems. In North America, devices using PowerG operate in the 915 megahertz ISM band. I believe in Europe, they also are variants of this that operate in the, 868 megahertz band, if I remember correctly. The protocols also advertised to have quite a long range. For example, they put out this YouTube video last year on demonstrating the range of this across Niagara Falls from US to Canada. And it's a interesting video, but they make some confident claims about the protocol. Aside from considering it one of the most secure protocols for alarm systems, they have a more detailed white paper type document giving some information about it. But overall, there's very little public information about it. What they do say is that it uses 128-bit AES, and they say it provides protections against intruders doing anything devious like grabbing codes and hackers substituting messages. These are, again, their exact wording, and they say it provides security and reliability comparable to a wired protocol without having wires. And they say that AES, being a well-respected security algorithm for encryption, it provides strong authentication and encryption in the protocol. But does it really? We'll see. Another thing is that PowerG makes use of frequency hopping, and they claim that it switches frequencies more frequently than an intruder would be able to retune. So their idea is that they have a hopping sequence that's derived from cryptographic keys, and this sequence should not be guessable by an attacker, and because it's frequency hopping, they claim that you cannot have an attacker sniff it. And they give some more detail around this, further indicating that it's the hopping sequence is dependent both on the current time and the encryption key and their algorithm for computing the hop sequence. So they say it's virtually impossible to sniff this thing. So we had encountered some devices with this, and we were wondering, what is PowerG doing? We had almost no information about this. FCC documents showed some internals of the devices and said it operated in the 915 megahertz band, but there wasn't very much information on the protocol itself beyond that. So we started off with some black box analysis of radio transmissions by these devices. So the first thing I saw is when I started sniffing just what's going over the air with an SDR, is that they're using GFSK modulation. You can see this from the shape of the modulation. With GFSK type modulation, you tend to have similarly rounded frequency distributions. There are still two peaks for where it tends to settle, so those peaks can still appear depending on the configuration of the modulation, but in general, this generally rounded shape for the distribution is just a Gaussian frequency shift keying for spectral efficiency there. And from the distance between these two peaks, you can see that they're 50 megahertz or 50 kilohertz apart. So that indicates a deviation of plus minus 25 kilohertz from the center frequency. Looking at transmissions, if you started demodulating the signal, looking at the demodulated signal, here I used SIGDigger to look at these. You can see that there was a preamble portion in the message here that was consisting of alternating 1 and 0 symbols. This is common in a lot of radio protocols for synchronization. And the spacing between these preamble symbols was 640 microseconds, which meant it's running at a symbol rate of 50,000 symbols per second. This plot particularly is showing the in-phase component here. It's when you look at the modulation, it's this is plotting one component of the sort of quadrature side. So you can really view it as a rotating complex number here. After the preamble, the next portion is the actual data body of the data. And so the modulation is not just an alternating back and forth 1 and 0 sequence, but it may have runs, and so that results in phase rotation. So that's why the values are shifting all over the place. Now, we're also looking at what is the frequency hopping doing here. So we ran an SDR looking at the whole 915 megahertz ISM band, and we saw 50 channels in use that were spaced 129.73 kilohertz apart. And they were ranging from 912.75 megahertz up to 919.106 megahertz. And the hop sequence did look random looking. It wasn't sequential or following a fixed skip like, say, the older hop sequence of Bluetooth low energy would did. It's random looking, and we saw there were packets sent to new channels 64 times per second. The next step after figuring that out was to figure out how are the packets structured. So there was some pretty consistent form to the packets we were seeing. First of all, everything was starting with a 32-bit preamble of just alternating ones and zeros. And after that, there was also another very consistent portion that was a sync word. And that, in big Endian, most significant bit first format is 1F, 3F, 1F, 3F, or 1F35, 1F35. And so that pattern is what's used by the radio hardware to synchronize and determine the start of the packet. For the next data after that, we were seeing repeating values, but it wasn't initially obvious what it was. Now, we noticed when we opened up the hardware, and I'll get to that a little bit later, that it was using Texas Instruments radio chips. And Texas Instruments has defined their own whitening scheme. And we were using the Universal Radio Hacker URH tool for poking at this. And I tried just enabling de-whitening using that TI CC1101 style whitening scheme supported by URH and supported by a lot of TI parts. And suddenly the message looked a lot more structured. And then it became pretty obvious that what followed the sync word was a length byte. And after that, it looked like there were some header values that, because they seemed consistent across a lot of packets, but there were certain bits that were getting flipped on some packets. Looking at the packet structure some more, we realized this is matching the TI standard packet format that's defined in some TI datasheets. This was originally used by some older TI radio chips and some of the newer chips. This particular product was using the CC1310. This same packet structure was defined in the datasheet as one of these supported standard formats. And in this operation, there was a particular type of CRC that was originally used by the CC1101 that newer TI chips use. And when we were looking at if we treated the next byte after the sync word as a length field, that was a single byte, and then we looked at the value that was at the end, that matched what was expected as a CRC. So this was confirmation that this is using the TI standard packet format. So after this, we want to understand the protocol in a little more detail. The hop sequence seemed random, and the payload data we were seeing also seemed high entropy and random looking. So we decided to start poking at the firmware to figure out what's happening inside these. The hardware that they're running on for at least the newer devices that PowerG modems use are TI CC1310. There are some older PowerG devices that use the CC1110. The 1110 was based on an 8051 core. The 1310 is using ARM Cortex M3. On there's also an additional radio core Cortex M0 that runs radio firmware from TI and ROM. There is some ROM patching mechanism in there, but that's not customized by the developers of this. They just had their own application code running in the main Cortex M3 protocol processor. And we noticed just from some initial examination of firmware binaries we saw on devices for these is they seem to be using TI RTOS and the TI Simple Link SDK. We noticed some strings that were also present in the TI SDKs, and that pointed us in the right direction. One nice thing is that TI is pretty open with the RTOS and SDK for these. It's a BSD licensed SDK, and we were able to just download that and see a lot of similarities in the firmware structure with TI's example code for these. So that made it easy for us to get started reversing this, even though we didn't have any symbols in this device itself. Here's an example what the hardware looks like for one of these sensor devices. The firmware is entirely on this one TI microcontroller chip there. This here, I believe, was a door opening sensor, but my memory is a little vague as I'd poked at this a year ago. For these sensors, they interfaced with a central device called a panel. And the main panel that's used by PowerG devices are the Colsys IQ panel. These are Android-based devices. They have a touchscreen on them. And inside, there is a daughter board that's a modem for PowerG, and it interfaces with the rest of the system over UART. The modem, opening it up, also contained CC1310 chip. Here's the inside of one of these panel devices. In red, the box there is the PowerG modem daughter board, and it's actually conveniently labeled as such as well. So, looking at these inside the modem, inside the panel's firmware binaries, we were seeing a whole bunch of different modem firmwares in there. We first need to figure out which is the right one in there, and we saw different firmware images. Some seem to be for an STM32, some seem to be for TI devices. There were very few strings in those, though there were some that were indicating TI SDK pieces within the firmware binaries that turned out to be for the modem device on this. There were multiple variants of the daughter board for the PowerG modem that were also registered with FCC. The newer boards had a lot of the details from the FCC data kept confidential, and chip IDs weren't obvious on the FCC listing data there, but poking at one of these devices here, we could realize it was a CC1310. So once we looked at the different binaries in there and saw one that seemed to be a CC1310 or some kind of TI SDK using binary, we then loaded it up into Ghidra and used SimGrate to identify known functions. And one of the particular function signatures that SimGrate was able to identify was a function with this very long name here, but it indicates it's a TI CC13X0, a hardware revision 20 and later. And by this, we're able to confirm it seems to be using the TI SDK and is a CC13XO chip. It was a CC1310 here. We were able to use that information to then map out all the peripherals that are being interacted by the firmware. And we were also able to identify the structure of the firmware, comparing it to examples of the SDK. It turned out they were using the IAR toolchain for building this, so we built TI's example programs with the IAR toolchain and compared the binaries we built that had symbols using SDK reference examples to this thing here. And from that, we were able to identify a lot of similarity in the structure, and again, assign names to a lot of the functions that we're being using to identify what's new and custom by the developers of this. We noticed that the data segment for the firmware was compressed, and we want to figure out how this is being done. IAR supports a whole bunch of different compression schemes. Looking through the early loading code to see how the data segment was getting initialized, we saw a little decompressor within the firmware. So I re-implemented that decompressor in Python and ran through it. Later, I realized this is just the LZ77 algorithm, and indeed the decompressor I made did the job and got us reasonable looking data for initial values for it. We also identified some command structures that the TI SDK uses for sending commands to the radio. The way the TI chips work is that there are a set of radio commands defined in ROM for the Cortex M0 core, and through a doorbell interface, you can tell the radio core, run commands, here's a struct with parameters for how you should do radio operations. So we found several data structures within the data segment here that were matching command numbers defined in the data sheet for this. And we found a whole array of these commands and just deciphered them based on the command structure definitions in the data sheet. So here's an example of one radio command. This is specifying what's the sync word to use, what's the specific command to issue. We saw the same sync word we saw in the black box RF analysis, so we knew we were definitely on the right track with the right radio commands. We then started looking for where is cryptography done in the firmware, and we found use of the AES crypto accelerator peripheral on the device. And it was being set up for use in AES counter mode, though the way they did counter mode was a little bit funky, which I'll get into. They were using software for implementing the counter mode, since it was a somewhat non-standard counter mode form. They were just using the hardware in ECB mode, where they would pass a block to operate, but they had software implementation of this somewhat strange counter. For talking to the Android side host of the system, there was a UART command interface. We saw a task in the firmware that's handling UART commands from the host. There were commands for configuring network keys and resetting the device and initiating pairing mode and things like that. There were also mechanisms for the modem to notify the host, the panel device, of any events that happened. The overall structure of the firmware, when we were looking at all the different tasks running there, once we identified the main that was setting up all the tasks in the RTOS, was something like this. There were tasks for handling message mailboxes from the host, as well as messages coming from the radio-related task. The radio task actually issued the radio commands, and these two tasks would communicate back and forth over sort of message queue type interface. So getting back to the crypto we were seeing in there, they had this custom counter mode-like implementation in there, but it was not quite the way AES counter mode is normally implemented. Usually you have a nonce and a counter that are concatenated, and that's what gets encrypted using fixed key, and then you XOR that with your plain text. Now, on every session, you should have a different nonce to ensure uniqueness and avoid some replayability issues. So for their form of AES counter mode, instead of a nonce, they had a fixed value they called a secondary key. And the data that's getting encrypted consisted of a 24-bit counter field, a 24-bit clock field, an 8-bit counter field, and the rest was this 96-bit secondary key, or zeros in certain instances. The clock field itself was only using 23 bits of that. The least significant bit was always 0 because of some rounding of the clock that was happening. The 64 hertz rate was resulting in that rounding, and that matches with the hop sequence. Notice the fixed key in there rather than a nonce, so we'll get back into issues on that. Now, they were using this construct of AES encounter mode for a few things. One was encrypting the payloads in the packets. They were XORing the data with the key stream from that. They were also using the same key stream for generating the channel hopping sequence. And they had also the very strange thing that they seemed to be calling a message authentication code, but wasn't really a message authentication code. They were just putting a couple bytes of the key stream in every message. And the receive logic was checking that the bytes of key stream in the message match what is expected. But this was not actually authenticating a payload in any way. So it wasn't really a message authentication code. You could still flip bits in the payload portion. They weren't protected by this. They were just CRC protected, which was I'm not sure what was in their mind when they were calling this a message authentication scheme. For the encryption, we saw logic for handling multiple encryption modes. There was one mode where it's not encrypted, and that's used for initial setup. And then there were other modes. One is using encryption, but with a network, with a secondary key of all zeros. That's the nonce portion. That's used in some modes for initial setup. It wasn't being used in the main communications we were seeing. And there was a third mode that had this fixed nonce, so-called secondary key, being used together with the main key being used for the AES encryption. And there was the 16-bit. In some places they called it a key stream check. In other places they were calling it a method authentication code from some strings in the firmware. And for unencrypted packets, it was all zeros, or all Fs. There was also that counter field in there. It incremented for every packet being sent within a certain hop event, and then it'll hop to the next channel and the counter will get reset. And it was a small counter, but usually not a lot of packets will get sent in any one hopping window. So it was a AES counter mode key generation for the channel hop scheme, and there were different modes for picking the channel you'd be hopping on, depending on some configuration. But in any case, it would compute a value and then do modulo of different bytes generated out of the AES. There was one mode we call hopping mode 2, where the channel was updated once every 4 seconds instead of 64 times per second, and that was used again in some initial setup operations, as well as situations where clocks get out of sync and they're trying to resynchronize devices. There was also one channel that was being used when devices are pairing or they have completely lost sync to reorient themselves. So, as I hinted earlier, this fixed secondary key was not really a nonce. If you have a fixed nonce, then you can do replay attacks, and if the same message is being sent at the same time, then you could notice that's happening. Now, they said, okay, it shouldn't be replayable because they have a clock in this data as well. But this clock they're using in there, that's 23 bits of real data, that's being incremented at 64 hertz. It loops over every 36 hours approximately. So, for that reason, any message you see at a point in time, if you see the same message 36 hours later, it'll have the exact, if it was sent at the right time, it'll have the exact same content. So this also gets to replayability of the protocol. Any data you captured going over there, you could capture it for 36 hours and then just replay it that time later, and it'll be perfectly valid. So this is definitely a problem in replayability and injectability. And also, with this not really message authentication that they have there, there's just CRC protection, which is trivial to forge, and you could flip any bits in the payload and inject them. So definitely problematic, and any captured messages you could just retransmit 36 hours later, flip some bits if you want, fix up the CRC, and you can convince the system anything's going on. You could inject, for example, if you sniffed messages to unlock the door lock, you could replay them 36 hours later, and your door lock will unlock. And yeah, this is quite replayable and malleable. Yeah, as I got at earlier, there's counter mode is very malleable. You can flip bits as you want. Sorry about this portion. Now, the gist of this here is that there is no integrity protection here. You could do whatever you want with flipping bits in these packets. The key stream check value you don't have to touch when you're manipulating the payload in the packets. And there's a repeating counter every 36 hours, so you could just replay old messages. So this in itself is a pretty broken encryption and authentication scheme here. But there is more that makes it worse. The panel itself was generating keys for the system, and the way it generated a key is just taking the serial number of the panel and flipping it backwards and treating that as an AES key directly. So it was just 96 bits of data, and the rest of the key were zeros, and it just took the backwards serial number as the AES key. And later they decided to improve the security of this. By the way, they used output or RAND, which is always consistent on Android every time you launch a process if you don't seed it. Later, they decided to improve the security of this. So we saw that there was a new firmware version they put out where they improved the security by multiplying each byte from the reverse serial number with RAND and then modulating it with 255, not 256, but 255 for some reason. So it's every byte is between 0 and 254, and it looks randomish by this silly manipulation with RAND here. And because RAND is not getting seeded with anything, it's not a cryptographic random number generator to begin with, but also they're not seeding it. In Android, it's by design consistent every time you call it in a new process. So it was just essentially manipulating with a static value. And so the keys used by all the PowerG devices are just based on the panel serial number. And also the panel serial numbers are all sequential and in a pretty small range. So if you get one device, see what the serial numbers are like, you can very quickly brute force through all possible serial numbers and figure out the key in use here. So that just makes this totally broken. The other issues with the 36-hour looping and injection malleability are more, you'd need to implement things a bit more and be patient. But with this weak key issue here, you could just break it trivially. We told the vendor about this issue early last year, and they just didn't respond to us for the longest time. And then we tried reaching them through one way, another way. I'll get into that. And today they still haven't fixed this issue. So all the PowerG devices out there are still using their serial number as their key. And yeah, this is a pretty popular device. I've seen it all over the place, these IQ panels and PowerG sensors. So this is a real issue and a little concerning that a lot of smart locks use these too. So knowing all these issues in the protocol, it would be nice to be able to capture it. So getting back at what they were saying earlier, they were saying, oh, we hop frequency so quickly, 64 times a second. No hacker can keep up. Well, you just sniff the whole ISM band. The whole band is just 6.5 megahertz wide. So you can just capture the whole thing with SDR and then do some channelizing to sniff all the channels. You don't even need to know how they're hopping. Again, because they're using weak keys, you can figure out the hop sequence, but you really don't need to know it because it's such a narrow band to begin with. So we just used an SDR to capture the whole thing, and then we used GNU Radio to do some channelization and burst detection of for identifying packets in there, and then implemented some demodulation of that. We also did some clock recovery in there to synchronize and sample at the right point in time on each channel to most miraculously get the right bytes. So this is a little tool we made with GNU Radio. You can see here on top is a little waterfall showing packets being coming out in different channels. From a specific burst here, you can see the spectrogram of it. It's time on the vertical axis. You can see the two lines off the center. Those are the frequency deviation peaks for the modulation. We demodulate it, and you can get symbols out of that. So we implemented all this with GNU Radio. I think some folks here may have taken software-defined radio trainings here, and I'm sure a lot of you have played with it. But the basic flow we used here was detect a burst, estimate the center frequency to correct for any clock drift. Then we did, in this particular implementation, we did filtering we brought the frequency off the burst down to the center frequency by mixing in software, and then did quadrature demodulation of the frequency modulated signal, clock recovery to identify the particular timing of the symbols based on the preamble, identify the sync word to identify the packet start, and then just output the bits from that to feed to a Python script. The structure of the packets that we saw is like this. There's, as I mentioned earlier, after the sync word, there's a length byte. Then there's some address fields after that. There's a header after that with various fields indicating configuration for the packet. There's that 2-byte keystream check value that is not really a MAC, and then the payload itself, which was the AES counter or counter-like mode encrypted, and then just the TI CRC after that. We then made a Python script to parse these bit streams, along with some additional metadata that we had our GNU Radio program spit out. So this tool here, we'll be releasing this probably next week or the week after that. Just polishing up some last bits to get it out here. This tool will identify based on a packet capture. The pairing process, by the way, for this just transmits the key in the clear. So if you're sniffing this protocol and during the initial pairing process, you could just be, if you have a sniffer running, you can capture the keys. Our utility will capture the pairing process if it's going over the air and just automatically figure out the key for you based on sniffing the pairing process. And then it'll also keep track of what the hop sequence should be and which hop mode it should be in based on which channel the data was observed on. We also added some decoding of particular fields in there and decoding of some decoding of the payload. Different sensor types have different payloads on them. For example, door sensors will have fairly simple payloads of door open or closed. Likewise for motion detector, when motion's detected. Some of the devices have more complex payloads, like the door locks have different message types that can go in different directions, both for lock status and also configuring things like pins as an alternate way to get in. So the pairing process on this, as I hinted at earlier, is pretty weak. It's a lot of protocols have done this in the past. Bluetooth Low Energy back in 2010 with their original pairing scheme also had the same type of issue, and this was common in older versions of Bluetooth and lots of other protocols. But embedded people used to think that asymmetric cryptography is expensive, so let's not do any of that. Let's just send a key over the air. Sometimes they will wrap a key with an additional static key, but the pairing process is insecure. It just sends the key over the air in clear text with a particular message ID on channel 15. So if you're sniffing that channel at the right time, you'll catch the key. Every time you add a new sensor to the network, you can the key goes over the air. You can sniff it. Once the key is exchanged, the next thing it does is it switches to the mode 2, where the secondary key, the nonce-like field, is kept at 0. At that time, there is clock synchronization messages that are sent back and forth, and the secondary key is sent over the air over this initially encrypted link, and then they'll switch to the next mode with the main secondary key in use. There are a few different message types. One of the most important ones was the data message type. There was a message type field in there that indicates the message type. Here's an example what the messages look like for the door sensor, where they show if a door is closed or open. There's also a bit to indicate tampering if the sensor is being opened or not. There was a tamper sensor in the switch. So this data here is after XORing with the keystream to decrypt it. There's just a bit field to indicate open and closed and tamper status. There's a bunch of things we could do in the future here that'd be interesting to poke at. The Johnson Controls likes to claim that their protocol is unjammable because it's frequency hopping. And that's really not the case for many reasons. Firstly, that's narrow enough a band that even if you knew nothing about the frequency hopping, you could just jam over that entire band in there. They do have an interesting jamming detection feature in there, but it doesn't seem particularly sophisticated. All it does, it looks for repeated packets received with an overly high RSSI. There are many forms of jamming that will not trigger high packet RSSIs. You could also do things like modulating the jamming, so you jam for a portion of the packet, then stop jamming, and then jam for a portion of the packet and stop jamming. But it's not particularly reliable jamming detection. In some instances, I was trying to trigger the jamming detection and failing, even though it was blocking the communication, so not very good jamming detection. There's also a substantial protocol attack surface. In this project, we were trying to figure out how the protocol works, and we didn't spend that much time analyzing the firmware to look for things like memory safety vulnerabilities. There's no fully implemented over-the-air firmware update mechanism in there, but there seem to be little pieces of it that were partly implemented in the firmware. And there's, in general, quite a bit of logic within the firmware for these. It's a mixture of C code for the firmware and C++ code on the panel side. It's plausible that there are memory safety issues in there. For instance, you could exploit to gain codec on these things. But anyway, with these weak keys, that's a minor issue relative to the whole system being wide open. We have disclosed 4 issues to the developers of the system. One was the weak pairing process with the keys going over there in the clear. One is a nonce reuse and replayability issues from that. One is the effective lack of message authentication, with that keystream check not being a message authentication code, despite their claims of it being that. And also the biggest doozy of these is the keys just being the serial number, or the serial number slightly manipulated with a static value. We identify these issues in firmware versions we looked at last year. We first told them of the issue in March last year, and they just didn't say anything. We were trying different ways of reaching them. We told their product security email, and they just didn't respond. We asked them, did you get it? You get it? Nope, no response. So then we went out to CERT and wanted to disclose that way. And CERT was able to make contact with Johnson Controls, and then they said, yeah, we got your report in March, but they just never responded to it. But at least through CERT, there was more pressure for them to do something, so we had a meeting with them, and they said, okay, I will do something. For many of the issues, they couldn't do much because it's just the design of the protocol itself, and all the sensors don't have updatable firmware. So protocol level issues they couldn't fix. But one thing they can fix is at least changing the key generation to not just use the panel serial number as the key. But there are problems there too, in that there's no mechanism the protocol provides for key updates or key rotation. So to fix this, what they said they'll do is they'll put out new panel firmware that uses a securely random key instead. They were saying that was supposed to come out in March. They said first it'll come in October last year. Then they said it'll come out in March. March passed by. Then they said, okay, we'll do some testing, and they just keep delaying. Maybe they'll eventually put out a firmware for this. But the other challenge is that to actually fix this, they have to unpair all the sensors and have someone go and manually repair every sensor and reset the system after installing this firmware update. So it's likely to be a long tail of trouble. Some of you may be interested in the tools we used here. One nifty SDR tool I like is SigDigger. It's something I've also contributed to. It's a handy tool for visualizing signals and doing some initial black box RF analysis. Universal Radio Hackers, another fantastic tool for analyzing black box radio protocols and then figuring out the structure of their packets. There's a lot of really handy tooling. The de-whitening tools in there are nice as well, and tools for figuring out packet structure. Firmware, we used Giedrich Reverse Engineer with SimGreat for identifying symbols based on known ones. New Radio we used for the packet capture tooling, and then Python, of course, for decoding scripts. And there were some Sandia laboratories, like New Radio utilities we're using for helping with the packet identification and demodulation. So that's all. Thank you.
All right. Thank you. Great talk. We have time for some questions.
So at the very beginning, you mentioned their little demo video of 1 kilometer range. What use case do they have for that?
I imagine they were trying to demonstrate both the reliability of the protocol and its suitability for large buildings. That 1 kilometer range only is effective with a line of sight. So one of the things they have is adaptive transmit power, where you can transmit with high power if needed for distant devices, and if things are nearby, they'll transmit with lower power. But it was for showing both their suitability for large buildings as well as reliability of the protocol.
Okay. And then, so you said fundamentally there's combination of protocol issues and crypto issues, and the expectation is that they can solve some of the crypto issues by changing how they do initial keying. But then you said because they don't actually have over-the-air firmware updates for a lot of the end sensor nodes, the window break sensors and stuff like that, presumably, does that mean these devices are going to be just kind of broken forever, and then you'd have to physically replace things with some new thing if they change the protocol in the future? And did they speak to at all anything about protocol level changes, not just crypto like keying changes that they intend to do in the future?
So I can't speak to their future products, but essentially with the existing products they have out there, while they can switch them to better network keys, the other issues are not really fixable without replacing products altogether.
Thank you.
Thanks, a great talk, and reminds me, it gives me many memories down the line. We've seen this for as long as I've been in this field. So the repeated key stream, especially, I remember that from the 90s. But and all of the other protocol things. The protocol, by the way, do you have any understanding of the history of the protocol? Like how long have they been using this, for example?
So this PowerG is their modern high security protocol. They sell products with their legacy protocol too, and they say PowerG was meant to provide upgraded security of their legacy protocol, but they still keep selling devices with their legacy S-line protocol as well. The first devices with PowerG were first rolled out, I think, around 2011 or 2012. But they've kept releasing new products based on PowerG, and it's still their
it's
flagship alarm system protocol.
Quite clear that no cryptographer was present. This was designed because we teach this at classroom.
It's very textbook issues.
Classroom. Yes. So another sort of so isn't there? I mean, given that these are security systems, isn't there like an industry body regulating security systems, something to do with like insurance or something? Wouldn't this be like an issue for them? Insurance premium going up because, it's just not secure.
So I'm not sure. I'm not aware of any body that's setting standards for security of these protocols. It's a case where there's a lot of really bad protocols and some are worse than others.
All right. I also have a question. So the protocol seems so broken, it's almost fun. You presented 3 ways: the weak pairing, the serial number brute force, and then the full key stream extraction. Yeah. Can you also get the key by just analyzing the frequency hopping, because that seemed to be also dependent on the key, or get the key from the MAC bytes inside the packets? Is that recoverable?
So the key stream, the portion of the key stream that they use for those not Mac bytes and for the what's it called for the hopping sequence was slightly modified. You may be able to recover up a portion of the key stream from the hopping sequence. The portion they're using for the key stream check portion is not a portion they use for the data encryption, but you can still recover the pattern of the key stream check bytes that should go over there.
Right, thank you.
Great talk. To answer that question about like security and protocols when it comes to access control, I don't know of anything out there. The access control, like some companies will validate that you're SOC 2 compliant or ISO 27001. But like in many industries, there also aren't really, there's like PCI compliance for credit card that doesn't really validate the security of a system, right? An implementation itself, but rather more like backend and corporate stuff. Yeah, but I mean, adding over the air doesn't make it secure either, right? So now there's a whole. It's just a child. Security is hard, right? So like you add OTA, and now you have to validate that those are cryptographically signed correctly. Mm. Yeah, but it's also more expensive than to actually buy those. Sorry. One other thing, the RSSI, it makes sense because the hardware like CC11 or 13 series, you're only getting RSSI ultimately on the on decoded packets, right? Hardware decoded packets, which means it has to be GFSK. It has to have a preamble. It has to have a sync word. So if you're jamming, as you noticed, you can like jam without hitting that and without triggering packets while still jamming, and then
like they'll capture things with an invalid CRC. They had it configured so that if you were having a wrong CRC but it was getting strong RSSI, it'll fail that. But you still need to be triggered. So they have actually one mode where they were operating where they would search for run a sync search. And then they were configuring the hardware to look for RSSI in that mode. It's similar to an example TI had made a while back that was using these chips as a spectrum analyzers, where they're just looking, they just configure the sync word search to never actually find anything, but still report the signal strength it's getting. There's a way to configure the hardware to do that, and they had some setup for that, but I was just never able to actually trigger it to actually think I'm jamming it. So if I can't trigger the jamming detection when I'm deliberately trying to jam it, then it's not very good jamming detection.
All right, sounds like there's room for discussion. We can do that later. There's one last question.
Could you give an overview really quickly again of that in authentication code that's not authentication code?
So what they do is inside every packet they put a chunk of the key stream. That chunk of the key stream is based on the current timestamp. So there's that counter that increments 64 times per second. They combine again the one counter, the timestamp, and the secondary key, and once they get some data, a portion of that key stream they include in the packet, and the other portion of it is used for the encryption of the packets. So it's not the same chunk of the key stream that's being used for the counter mode XOR, but it is the counter mode key stream output. A chunk of that is being used for the actual chunk there. So what it does achieve is that if you don't know what that should be and can't inject it, then you don't have the right key stream for the chunk of time. So you can't just inject an arbitrary packet without that key stream chunk being right, but it's not tied in any way to the contents of the packet.
And AES is being used to generate the key stream?
Yes.
All right, let's thank the speaker again.